is a good friend of the Simon Center. He's here for a few months on sabbatical, and he's coming back again next year. We hope he will continue coming every year. He's an excellent lecturer, an excellent physicist. And in fact, he's probably written the shortest and most beautiful introduction to fluid dynamics. I get no royalties, but if you want to buy a good short book that you can travel around with, buy it.
Yeah.
Please, Richard.
Thank you, Luis. It is this book, and because I wrote everything here. You don't need to buy it. The person who asks the best question or gives the best answer at the last lecture will get it as a present. I have only one, but it's also I'll be looking here from time to time because the moment you write something into a book, you can forget it. That's your external memory. Okay, good. So I'll try to give introduction and not as we give it to students, undergraduates, namely, here is a knowledge, you need to learn this knowledge. I'll try to talk to you as to fellow researchers in a sense that I'll try to, together with you, kind of, invent fluid mechanics to show. It will be very, very kind of elementary, but it's really what's most interesting is that how it is done, and the next thing, what is not yet done, even though I'll try to be elementary. And also, particularly for graduate students, I want to train you intuition, because fluid mechanics is such a beautiful subject, which is a field theory. It's a field theory, not quantum, it's classical field theory, but it's also mechanics, which means that mechanics, we have intuition about it. We know about pushing things, turning things, and all this. So it is something in which you can really develop physical intuition. And this is why I really want it to be interactive. So I'll be asking question, pausing, and then, I'm a former actor, so I can keep a pause until somebody answers it. And it could be a wrong answer. And I very much advise you, the way that I advise my students at Weizmann, give answer immediately. Not necessarily aloud, you can give it to yourself, but whatever physical question, give answer immediately. Then ask yourself why actually you have given this answer, and then this is the way you train your intuition, okay? Good. So fluid mechanics, as I said, it's a field theory, which means that we'll be talking about continuous medium, which means that every property of the smallest fraction is the same as property of anything else. So we'll be talking about fields. So we characterize this medium by a velocity, which is a vector field, which would be a function of another vector field and time. And we'll be talking about density of this fluid, which also will be a field. And it's a continuous medium, and density would satisfy continuity equation, namely that we say that if we take any volume and we integrate density over this volume, and we differentiate it, then it must be an integral of some flux out of this volume. And df would be an element of an area which is a vector directed outwards. And so now by Stokes' theorem, we can say that d rho dt satisfies continuity equation. And this is our first equation.
Can I ask you a question?
Yes? Yes.
Can any of the field theory be derived from an atomic description?
No. No. Because fluid mechanics, the beauty of fluid mechanics, that it does not care whatever atoms, molecules, polymers, or people are actually moving.
How do you actually know that? Why doesn't the belief in those assumptions depend upon some property of the interactions of the molecules?
I don't know. That's the way physicists do. I assume and then I check consequences. And sometimes it works and sometimes it does not. And I'll tell you when it does not from few cases. But just to give you an example, turbulence, the word turbulence, which is fluid mechanical phenomenon, comes from the word turba, which is a crowd in Latin. So it is as much relates to people and collective motion of people as of molecules, polymers, particles, whatever. Okay? So I'll try to be very, very phenomenological. And essentially, as you will see, fluid mechanics is a set of conservation law. This is a conservation law, right? This is something, the integral of rho dr conserved. It's also, I can write it in a form like every mass of a fluid particle is conserved. So mostly it will be set of conservation law. A conservation law are notoriously robust with respect to, but we'll see some conservation law broken, we'll see anomalies, and this is the beauty of fluid mechanics and why we like it so much, that almost all things that we have in field theory, renormalization, anomalies, etc., appear already there, and actually first time appeared in fluid mechanics. But no atoms, no molecules. Okay, good. Now, if we look at this equation, we ask what property we need to impose on velocity. If it satisfies this equation, at least first special derivative of velocity must be finite. Otherwise, this equation does not make much sense. So we assume not only continuous medium, but we also assume what is called continuous motion. And which means that this velocity, as a function of its special coordinate, will be assumed to be not only continuous, but have it finite first derivatives. Namely, in this tensor, all elements are supposed to be finite. Again, it's an assumption. Can I prove it? If you can prove it, you get $1 million. That's a subject of a Millennium Claim Prize. And it's formulated as follows. You impose initial condition on the equation which I did not yet write, which in a moment will write. It will be equation, just Newton equation, time derivative of velocity acceleration equal to force. So the question is, you impose initial condition which satisfy this finite. How long it will be? Is it possible that during a finite time, this condition will be violated, and some of the derivatives will turn into infinity in a finite time? As we later on the lecture, actually 3, will start talking about turbulence, we'll see that statistically, when we look at the statistical properties of a turbulent velocity field, it is violated. Still, we don't know if any flow dynamically in a finite time loses its smoothness. Okay? So this is a continuous motion, so we make this assumption, we'll work with it, we'll see how it works and how long it will survive. This is a typical way you do phenomenological science. Okay, good. Statistically means that there are some moments of velocity field. Let's say something like you take velocity at point 1, you take velocity at point 2, you take modulus, you take square, whatever. Moment, and you ask if it's R12 in the power, the answer is no. Okay? On one hand, it could be that the measure slowly goes to 0 as you approach singular realization, or it could be that singular realization actually has probability 1, which is Millennium ASCII. Okay? So statistic does not yet mean that you dynamically violate it. There are two ways, and we don't know which one is true. Okay? Good. So, okay, now we need to write an equation on velocity, which must be a Newton equation for acceleration equal to force divided by mass. Now, everything we'll be doing, I'll try to use both physicists' approaches. On the one hand, it's field theory, so we'll be writing equations on fields, you know, with partial derivatives in space, partial derivatives in time. On the other hand, it's mechanics, which means that we have a very powerful formalism, intuition of fluid particles, right? So now, what I will, before writing it, I ask, what makes fluid flow? Why it's fluid? And what we call fluid? What's the definition of fluids? Anybody could give me just intuitively, the way you understand. What is fluid?
Particles with coordinated motion?
No particles. It's a medium.
A medium with coordinated motion.
A medium with coordinated motion. Is this coordinated motion? I mean, all particles in this piece of chalk move simultaneously together. So fluid is not about moving together. Okay, good. So Any other attempt? What is fluid? Fluid is gas, liquid, plasma, swarm of people, of birds, a school of fish. How would you define what is fluid? What makes this solid and the water in a glass, I mean, then this fluid? What makes it? What makes it fluid, which is there? Yes?
Probably because the characteristic length scale should be larger than the length scale of the particles, composite particles.
I can consider this on a length scale much larger than particle and still, yes?
A system whose mass and volume also change in time?
Volume, aha, okay. Now we start in talking. This is not volume, but shape. Shape, okay?
Liquid gases as well.
Okay. That if I really open it, which I don't want to do, and start that, you see that the shape would change from this into that, right? So fluid is something which can change its shape under action of what force? What we need to put fluid into a motion, this fluid? It's under forces, right? Now forces act on this fluid. There's gravity, there is a resistance. So
There should be a gradient.
there should be a gradient of force. Okay, there is a gradient of force. Pressure here is lower than pressure here. You take and you just dive into a pool and you see how much gradient of force you experience when you dive 5 meters down. I actually tried it. You feel it here. So there is a gradient of force, but it's not enough. The force must have a very special direction. Okay, so why fluid does not move in a glass and then move in a windshield? On a windshield, fluid moves. In a glass, it does not. Even though there are forces there, and gradients are there and there. So what's the difference?
So shear?
Yes, it's a tangential forces which make it move, and normal forces which does not. Okay, that's the main part of a definition what is fluid. It cannot sustain tangential forces. Okay, now is this fluid, which I just called solid 3 minutes ago? I'm asking, which means that it's maybe a little bit more to it. Yes?
Solid because it can withstand shear forces. It has a resistance to all tangential.
Can it withstand shear force? That's exactly the question I asked. So I take liquid water, I put it on a windshield. It has shear force which is parallel to surface, and it moves. Now I take this, I put a shear force on it. Will it move?
Not easily.
Yes, it will for 1,000 years. Okay, just look at any glass, etc. So, of course, any crystal lattice at a finite temperature has defects. The moment you apply a force, those defects start moving, and material will be moving. Everything flows. The matter is a time scale. In the Bible, there is in the Judges 5, the Deborah prophetess says that mountain flowed before the God. So everything is a matter of a time scale. If you have a proper time scale, then you see mountain flowing, you see continents flowing, etc. So we call fluid something for which the observation time is comparable or larger than the relaxation time. Okay? That's the only definition.
How do you discriminate between fluid and solid when there is no force?
When there is no force, I don't know if it's fluid or not. Moreover, as I already said, every material is fluid because there is a very delicate question. If you take ideal crystal at 0 temperature and apply to it infinitesimal force, I don't know the answer, by the way. Will it flow or not? Any matter, crystal, amorphous, gas, under forces which are stress will move. If I am observing it long enough, I call it fluid. That's the definition. Okay? So now you see, how ambitious we fluid mechanicists are. We just kind of embrace everything. Okay, so now as we are going to write the equation, which will be, would like again to take this, I will be calling it fluid particle. So just an enclosed piece of a fluid, infinitesimal, but it's continuous medium, and I would like to write a derivative of its velocity, and it must be force divided by mass. Okay, that's Newton's law. So now when I think about forces, as I say, that if I am at statics or in a state of a uniform motion, there are no tangential stresses, which means that whatever plane I take inside my fluid, all the forces are normal to this plane. There's no forces tangential, otherwise it could not be in statics. Now I want to consider a flow which is not that far from, being at rest. So I won't neglect tangential forces, and it's a very, very powerful assumption. It tells me that out of a stress tensor, which in 3D is 9-component tensor, stress tensor is how much force in this direction is applied to a surface with normal to this direction. I won't treat only diagonal component of this tensor. And it's a nice exercise, which is called Pascal law, and I really don't want to do it. You generally do it in the high school, Pascal law, which tells that if you have only diagonal parts of stress tensor, then all three components are equal to each other. It's a very nice exercise in geometry to prove it, which means that we describe the state of stresses when there are only diagonal stresses by a single scalar quantity, which is called pressure. And again, which means that if I take this fluid element and I again define the normal, then I say that P dF would be force acting on it. So pressure is a force per unit area, and so my dV dt must be equal. Oh, sorry. Okay. So what I'm saying is that the force is an integral of pressure over area, and this must be equal to dV dt. The integral, and I can also write it as an integral of gradient pressure over volume. Okay, so my dV dt is minus gradient pressure over density. That's my mass, and this is minus is because pressure always assumed to be acting outside, which means that what acts from outside is minus pressure. So that's it. So I'll probably won't use this one. So let me keep it here. That's an equation which was written by Euler in 1755 and then 57 in Petersburg and Berlin. And the genius of Euler was this term. He realized that the pressure is a field, that there is a pressure inside the fluid, because before, when Bernoulli formulated hydrodynamics, the pressure was something which was applied from outside the fluid. And Euler actually considered it a B field. Now I neglected tangential stresses. Before we really accounted for them and see what is the parameter, let's guess. So for uniform flow, it's okay to neglect tangential stresses. There is none, right? They appear because of a relative motion of a fluid layers with respect to each other. That would be mutual friction between them. It will be forces. So there would be mass criterion imposed on a velocity field V, right? What would we expect it? That we require something to be smaller than something. What is it? To say that I can neglect these forces. Velocity is not. Velocity could be any, right? If velocity is large uniform, I just, okay, no tangential force.
The rate of change has to be really small, or the rate of change has to be
The gradient, yeah. So a natural assumption is that something like, if I have, I don't know, a body of a size r moving with velocity u, so something u over r, which is a typical grad v, right, must be small. Let's keep it in mind, and then we'll return to it and see that it's not. Okay, good. So now I want to write this equation. This is written in a form which is a particle type mechanics, which is called Lagrangian in fluid mechanics, even though also Euler wrote it. It still is called Lagrangian. So I may now turn it into a field type form with a special derivative, because what is this dv? You know, any dv during time t would be dv dt dt plus dv dre delta re, but this would be vi dt, right? So if I now divide it by dt, divided by dt, divided by dt, there will be this, right? Which is called material derivative or extended derivative, which essentially, why you're smiling? Yeah, I'm not a field theorist. Okay, I'm a fluid mechanicist, so kind of, which means that it's dv dt plus v grad v equal to minus grad p over rho plus whatever forces. For example, you have gravity, you put here gravity acceleration if you need. Now, because it's the second law of mechanics, yes, second law of Newton, we can of course write it as a conservation of momentum, right? So momentum is rho v. So I can write again, because momentum is conserved, it must be a divergency of a momentum flux. You then advise me about right notations, because I really want to learn to use proper notations for different audience. Now, what is this if I look here? I would immediately see that it's pressure, which is a diagonal part of it. And then I would have, which would give me this term if I also invoke continuity equation. Okay? It's a usual way you turn Lagrangian particle description into Eulerian field description. This is a system of coordinates fixed in space, right? Everything is partial derivative with respect to t under a given coordinate or with respect to r under a given time. And this is the Lagrangian description. This is with the flow. It's in the comoving reference frame. Okay, so now I want to understand what kind of a non-diagonal part would be, right? And again, it could be anything, right? So for this piece of so-called solid on our time scale, it could be a pretty complicated thing. And also there are many things which gels should treat as fluid, but they have a very complicated relation. But we expect that this something which must depend on V, and also not on V, because as we discussed, homogeneous V does not produce anything. It would depend on dVA over dxk derivative, right? And again, we assume that we do not have very large gradients of velocity. We assume that those gradients are small, or typical scales of velocity change are large, comparing to what? What is a scale with which typical scale of velocity change must be large so that I can, in this consideration, restrict myself just by first term of expansion. What is a scale here? What provides friction physically?
The formation scale? The formation?
What is deformation scale?
Oh, I mean, let's say, for example, you take a cube, okay? And you move, for example, the cube, let's say the upper hip, a little bit. So you twist essentially you deform essentially the element. Okay? So
This is something which is related to internal properties of the material.
Microscopic defects.
For example, macroscopic defects. Being in a gas. In a gas, what it would be in a gas?
The interaction between the particles.
Mean free pass, it's called.
Yeah.
So you see, we are back to particles on a very kind of superficial level. So we need to say that somehow we need to assume, because indeed what brings force from this layer to that layer? If you are in a gas and your layer of gas is flowing, it's molecules which physically come from here down there, and they bring momentum from here down there, right? So let's try to estimate the coefficient between which relates force. This is actually not force, this is force, right? This is the momentum flux, is a momentum transfer rate per unit area per unit time, okay? So let's assume again the simple type of a shear flow. So I have my v, x, which is a function of y, which is, I don't know, k, y. And so I'll take this line and I ask how much I bring momentum from here to there. I just want to get momentum flux. Okay? So momentum flux would be mass of a particle, concentration of a particle. This is actually rho. Okay? Times what? Times typical velocity of a particle. For a gas, it will be just thermal velocity. Okay? And then times the momentum difference between this and this. But what is the scale on which I take it? Like you rightly say, it must be scale which is the mean free path times the gradient of v. That would be my momentum flux, and that would be my viscosity, namely the proportionality coefficient between momentum flux, which is stress tensor, and velocity gradient. Okay? This essentially goes back to Newton, and that's why such fluids are called Newtonian fluids. Polymer fluids aren't like this, for example. They have their internal elasticity. And if we now divide, this is called eta, it's called dynamic viscosity. And we most often will be working with eta over rho, which is nu, which is called kinematic viscosity. And it has a dimensionality centimeter square per second. It's just a diffusivity. Apparently, everything which for gases, what we did, the estimated for gases, is a typical velocity times typical mean free path. For example, for what I talked at colloquium last week was about that we're now applying it to electrons, and this is Fermi velocity, and this is the mean free path, and not necessarily of electron-electron interaction. It could be a mean free path of any scattering which conserves momentum, because this comes out of momentum conserving interaction. Molecules just bring momentum from one place to another. They don't lose it. They just bring it from one another. Now, now one can see how it depends on different parameters. For example, if you take it and heat it, then your V increases, and L practically does not change, because this is something which depends on concentration, sigma scattering cross-section. So this is something which changes with concentration. This is something which changes with temperature, right? So when you heat the gas, its viscosity increases. And when you compress it, when you decrease L, its viscosity decreases. This is something which was a big surprise for condensed matter people working with electrons, that when you really, and which is well known to engineers. Okay, but those are gases. Now liquids. What do we expect of liquids? You take a liquid, you heat it, what do you expect from its viscosity? Exactly, because the mean free path, it's your step. If you keep velocity, for example, right, you keep temperature, or you keep concentration for, because for electrons it's other way around. If this is Fermi, velocity depends only on concentration, but this is mean free path, it depends on temperature, because it's an interaction between them. Anyway, you increase density, you decrease mean free path, you need more steps, your diffusivity is less. This is diffusivity. For liquids, you cook, you just pour oil on a pan, heat it. Viscosity is larger or smaller?
Decreases as you heat it.
And for gas it increases. Why? Could be physically. Well, we all know, I mean, at least those people who have seen. So for liquids, the mechanism of momentum transfer is totally different from molecules physically coming from here to here. This is a gas mechanism, right? So for molecules, is actually what brings momentum is an interaction between molecules. Liquids are practically incompressible, their density doesn't change, and molecules don't travel much. I mean, they're already packed practically with the density of a crystal, they're just inhomogeneous. So when you heat them, they interact weaker, and so this formula does not work. This is a gas formula only, okay?
What's confusing is that in terms of a phase diagram, you can go continuously from quote, gas to liquid, and there's no difference. So why are you making a distinction between gas and liquids when it could be continuously?
This distinction disappears at a critical point, and as I approach critical point, this formula works less and less and less, and the distinction between gas and liquid disappears. But when I am far from a critical point, this is a big distinction, and in particular, the viscosity depends oppositely from. So you take the same molecules, you compress them into liquid, then when you heat them, the viscosity is less. But you can cool liquid even more, viscosity will increase, and increase, and increase, and then what?
Solidification.
And then you come to a freezing point. And so you expect your velocity to turn into infinity and give me a clear difference between liquid and solid, right? And I just told you there is none, right? Which tells you how actually delicate this point of freezing and creating a solid, and how much the idea of a time scale on which you are doing it is important. So again, while we're working on normal time scale, okay, and we really see viscosity going and growing with cooling, and eventually turning into what physically for us is infinity, and we say, okay, look, this is a freezing point, that's where our liquid turns into a solid, or into amorphous. But then again, for amorphous materials, we know how important is the process, the rate with which we are cooling material up to a given temperature. It very much dependent on what the behavior will be of our viscosity. Okay, good. So now we are ready to add to this equation the another part. The only thing that I did it here in pretending that this is scalar and this is scalar, and of course they are not. So essentially what I have a tensor, and I have another tensor. And generally, I need to put here a fourth rank tensor. And if that would be true, I would not be lecturing here because normal fluid mechanics is scared to death already of a second rank tensor. So what saves the day? Why it's actually what is here is just this one, well, just a scalar constant and not a fourth rank tensor. Try to guess. Huh?
The normal terms cancel. The normal terms cancel out.
What means normal?
The
You mean divergence? You mean dl? You know, just for simplicity and because we have enough trouble already, let's make fluid incompressible. Okay. So we make fluid incompressible, which technically means that velocity is much less than the speed of sound. But out of this equation will be just diff v equal to 0. It's a rate of change of volume. We assume it's 0. Rho from now on equal to unity. Let's make life easier. Okay. So there is only, if you compress here, you expand here. But you can also shear. And you can also rotate. There are 9 components in this tensor. I mean, this is a big thing. I mean, even with divergence, with a trace being 0, you still have 8 components here. It's a lot of trouble. So what are the properties? And there are very fundamental physical properties. Yes? Symmetries. Which kind of symmetries we expect from stress tensor first? From a flux. Well, let's go to the other side. This would be symmetry side, and that would be dynamic side. Okay? So, do we assume it's symmetric? A simple case. Cij. Would we assume it? I'm asking all the time because I'm trying to build fluid mechanics with you because there is a lot of things which you assume something, then it works, you assume something, then it does not. And you learn a lot in the process. We want it to be symmetric. Think about it. What does it mean symmetric? So consider an element x, z. So we have here an area with a normal looking to z, and what acts on it, I mean, what flows is sigma xz. The same here is sigma zx, right? What would be the meaning of it be symmetric? That locally, when I consider this element, they do not rotate it. Okay? Now, let's write the equation on this rotation. So, if, for example, I assume rotation around this point, okay? So that's my distance to the axis of this force. This is my distance to the axis of that force. So if I write sigma xz minus sigma zx, and I multiply it by area, which for this guy, my area would be delta x times delta y. And distance to the axis will be delta z. The same for this guy. The area would be delta y and delta x, and the distance would be delta x. So this is the momentum of forces acting on it, and it must be equal to what? To the momentum of inertia times time derivative of the angular frequency. And momentum of inertia would be delta x squared plus delta z squared, and it must be d omega dt. That's the equation. Why? It immediately tells me that this must be a symmetric tensor. There is conservation of angular momentum. Yeah, this is a statement that the change of angular momentum equal to the momentum of forces acting on it. But I am writing it for infinitesimal element. I am looking at this at the same point here. At different points, they could be different. But I'm trying to tell you that if I take it in a given point, this would be my, this component would be, look, this is 1, 2, 3 small distances, and this is 2. So when my delta x, delta y, delta z go to 0, if this is finite, this is infinite. Okay? So to prevent infinite angular acceleration, my stress tensor must be symmetric. This is a very happy coincidence, but I also still need to say something about, where is my another guy? This. And this tensor has also 2 components. As we say, well, this one is gone, so it has 8 components, and I can divide it into a symmetric part.
So I'm confused. There are 3 powers of length on one side and 2 on the other.
Yes. So when my deltas goes to 0, this goes faster than this.
Yes.
Okay? Which means that you, if you...
Sigma is fine, then delta omega is
You also
0.
Yeah.
in the right state.
Huh?
You also need to mask film.
Yeah, I forgot my mass. Sorry, that's a very good remark, because I already wrote it once, and now, and then I forgot it. So what I forgot here is that this is not an inertia tensor. I need to multiply it by mass, which is rho. Thank you. Thank you. Yeah, that's really important. Yeah. So I have the same element here, but this axis would give me this infinite if this is finite. Yeah. Okay. Now I'm back to my right side of this, and I'm saying that this has this and I can also write it as an antisymmetric part. This is called strain or rate of strain sometimes, and this is called vorticity. Both are very important, and I spent a few moments on this kind of kinematics, what it physically means. It's also called omega. It's called omega as a vector, even though it's a tensor, but in 3D, as we know, there's antisymmetric has 3 components, and it's like I can pretend that it's pseudo-vector, but this is a true tensor, and it's called SIK. What is the meaning of this tensor? Again, if I consider an element which I just, so if I take such an element, and let's say I count all velocities from here, then the velocity in this direction here will be dvx over dz delta z, right? And it would be a relative motion of this point to that point, which means that with the time it will be turning this straight line into that straight line. The same here, if I would look at dvz dx delta x, this would turn this line into that line. So the sum of these 2 components is a rate of deformation of any rectangle into parallelogram. This is the this symmetric part is the rate of deformation of my element, right? This is what it does. On the other hand, omega is clear. It's antisymmetric part. It just tells me that for any such vector, there will be a motion perpendicular to it. So this is a rotation of a fluid element. For example, this famous and our favorite example, which will be taken over and over, the shear flow, for which I have only dvx over dz. It has vorticity and strain exactly equal to each other, right? So if you look at this formula, each one just give you. So in this case, what you do, any element, you rotate and deform with the same rate. Okay? So that's a kinematics of tensor of velocity derivatives. And now we need to understand which one or in which proportion they would enter into this beautiful symmetric tensor. And the reason that we need to really understand in what case there will be a friction between layers or momentum transfer from layer to layer. Consider separately vorticity. Vorticity means that locally you give a rotation rate, so your velocity would be linear function of a radius from a given point, and your angular velocity will be a vorticity, half vorticity. Would it be friction of fluid layers one with respect to another? Absolutely. Yeah. It's a solid body rotation. So when you just vorticity locally, define U solid body rotation. And solid body rotation does not produce friction and relative motion of a fluid layers, which means that only symmetric part of this tensor comes into the determining forces. And that's the beauty of it. Because now we say that if I have two symmetric tensors in the isotropic medium, I can always find orthogonal transformation, namely I can find such a reference frame in which they would be diagonal simultaneously in the isotropic medium, and in particularly because I assumed that there are divergence of it is 0, then there is just and that's what Newton realized God knows how many years ago, and that's why if there is a compressible fluid, you also add here a divergence term. Okay. Now, when we where is my So now I plug it here. And eventually, for incompressible fluid, I rewrite it in the following form. In the earlier form, and it's called Navier-Stokes equation. It's a very it's the only example in science, at least in physics for sure. It's called Navier-Stokes, and Navier was the first who derived it, and Stokes was the last who derived it. And there were 4 people in between for sure, because Stokes referred to all of them. And there is a very interesting historical subject for which I've heard was 1-hour lecture. It was fascinatingly interesting why we actually call it this name. But this is what is called. It's Navier-Stokes equation. You see that indeed this term is a diffusion. This is a vector field, right? It's a diffusion of momentum. Every component diffuses with the diffusivity nu. And now we may answer when exactly this term is relevant, right? With what we need to compare it. With other terms, right? Well, sometimes it could be a rhetorical question, but rhetorical questions also need to be answered. Right? So if you would, let's say, work without this term, which we'll do at the beginning of next lecture, which is called idiocy of ideal fluid, maybe an important historical remark here. When Euler wrote this equation, he was totally ecstatic initially, because first of all, it's just first order equation, and second, you can take a curl of it, right? Turn it to the equation for vorticity, and then you can prove what we'll do at the beginning of next lecture, Kelvin's theorem, that if vorticity is 0, it stays 0. Aha, said Euler, let's assume that velocity is a gradient, is a potential flow, is a gradient of scalar function. Then you immediately turn it into what is called Bernoulli equation, which tells you how P and rho v squared over 2 are conserved along any trajectory, and it was kind of, you're doing field theory with a single scalar field, right? With a potential and pressure, which is essentially one scalar field. And after probably a year, he realized that vorticity is unavoidable, and then he realized that he cannot find any meaningful solution. And for now, if you look at the book, which is called Analytic Solution of Navier-Stokes Equation, it's not that, it's that book. Okay? So essentially, what I'm saying now is that if you are in an ideal fluid, this and this term has essentially the same scaling. Like, this is just, it's a grad v squared, to put it simply. It's a grad v squared. So when now you compare this term, and again, as we discussed, so we, over here we discussed. So if I have body of a size r moving with a velocity u, I can estimate this term, which is essentially inertia. This is inertia term. If there would be no forces, my fluid would move by inertia. Every fluid particle would keep its velocity. Okay? So we compare inertia, which is u squared over r, and we compare it to nu u over r squared. And the dimensionless parameter here is a famous Reynolds number. I want to start new blackboard because we're finishing, and I want to finish it here. So now our dimensionless parameter is u r over nu. When this is large, you can neglect tangential stresses. Well, most of 20th century we spent on proving ourselves that anomalies appear. We cannot neglect them because you cannot neglect Laplacian. It's like neglect Planck constant, which is essentially Planck constant is also coefficient in front of Laplacian, right? So, but at least kind of when you naively look at this equation, you see that it's not u over r, it's ur, which is a parameter, because you need to compare it with diffusivity. That's a parameter of your medium, and so when you ask what is the parameter of my flow, for which I can neglect tangential stresses, it's ur and not u over r. And if, for example, you consider it for gases, this nu, and this is VTL, you see that essentially your dimensionless parameter, which determines the relative role of inertia and friction, is your velocity divided by, this is actually speed of sound for gas, right? Thermal velocity inside. For, again, for electrons will be V Fermi, but for most materials that would be more or less, well, for fluids in a normal sense. And this is mean free path, you see? So on one hand, this is by assumption huge, right? We're in a continuous medium, which means that this is large by definition. But this parameter not necessarily large, because this could be very small. Okay? So this is why fluid mechanics actually exist in the whole interval. And that's why it's so interesting, that the fact that we are in a continuous medium approximation, namely r, any scale much larger than mean free path, anything molecular standing here does not mean that our inertia is more important than friction. This could be very small, and it is actually very small. Okay, so I want to finish at this point, maybe just to last, because it's like from a birthday. Someone needs to bring something home, right? So just to give you this new maybe you don't care much for electrons, but this is something which really every human need to appreciate. This is something about everyday life. Air is 15 times more viscous kinematically than water. Because this nu is a diffusivity. It tells you, if you take a vortex of the size 1 meter and you ask how long it, or I don't know, 10 centimeters, how long it would take to diffuse, it would happen in water 15 times longer than in air. Dynamically, of course, the forces are much more in water because the density is larger. But kinematically, you don't care. That's why vortices and many different phenomena in water are so long-living. Yeah? You see ship passing and you see the vortices, or you see plane flowing, and these vortices actually diffuse much faster than you see them in water. Okay? That's just to give you a feeling. Okay, that's it for today. Questions? Questions? Yes, first questions and then thank you. That's trying to evade questions. Well, I have questions. First of all, I have a question. I assume that you, Zor. Yes.
In high school, usually we say that something is friction when it loses momentum. And here you ascribe trick. You say you use the word friction, the momentum is conserved. I didn't finish the equation of conservation of momentum.
Yes, it's a
Question about terminology.
Yeah, you're right. So terminologically, we also say friction. Let's say bottom friction, and that's how you lose momentum, which goes to the bottom. Or we say wall friction, it's how you lose momentum when it goes to. When we say internal friction, which is viscosity, it means that your momentum goes from layer to layer inside the fluid. So this kind of terminology, it's still not very good. So I would.
Also, the word dissipation.
I prefer. I did not talk about dissipation. It's energy. There is no dissipation so far. Momentum is conserved, and I did not talk about energy. It will be next time. Energy is dissipated, but momentum just diffuses. So I prefer diffusion. So there is a friction when you lose momentum to outside, and there is diffusion when it's clear that it's conserving. Just diffuses from place to place, terminologically. Okay.
I would say that if you start from a microscopic theory of molecules, of course, also energy is conserved.
Yes. So then I will be, yeah, that's right. But that's why I don't like particles. But then again, I can say that energy goes from this part to this part, and I can always treat my system as closed. I am assuming that you did not know anything about fluid mechanics, so you're infinitely ignorant and infinitely smart. So I'm moving pretty fast, but I'm starting from very elementary, right? And if you want me to change it, that's up to you. You can say, okay, go, this we know. Or slower, that's whatever, slower. Okay? So I very much count on your feedback. Okay? And it could be also done not here, just by sending email. And I'm here on the third floor. Questions? Good. So see you next week at the same time. It's coffee time, yeah. Anyway, we always need to finish in time.